Hello, my name is Ariana Capati, an uprising junior at the University of Maryland, College Park. These past few weeks, I have been enrolled in a Python course where I was taught an introduction to structured programming, computational methods, and data analysis techniques with the goal of building a foundation to allow students like me to confidently address problems in research and industry. Fundamentals of programming, algorithms, and simulation were covered from a general computer science perspective, while the applied data analysis and visualization portion make use of Jupyter Notebook and Spider software. I will be giving a brief review of the entirety of the content covered in this class. So this is Python for data analysis, the final review. So the table of contents. We'll be going over 8 sections, first starting with getting started. Getting started. Installing or updating Python on your system is the first step to becoming a Python developer. There are many ways you can get started with setup and installation. You can download the official Python distributions from python.org or install from a package manager called Anaconda, and even install specialized distributions for scientific computing, Internet of Things, and embedded systems. Python arithmetic. Python allows you to perform all of the basic mathematical computations that you can perform on a calculator, using syntax similar to what you'd expect if you were using a calculator. To perform arithmetic with Python, simply type the operation you wish to perform into a code cell and then run the cell to view the result. The following arithmetic is shown below. I especially want to emphasize the 2 division signs that are used for floor division, which round decimal remainders down, 2 asterisks for exponentiation, and lastly, the modulus operator used by the percent sign. The modulus produces the remainder you get when dividing 2 numbers. Math expressions in Python follow the normal arithmetic order of operations, so multiplication and division are executed before addition and subtraction, and exponentiation is executed before multiplication and division. You can use parentheses in your math expressions to ensure that operations are carried out in the correct order. Operations within parentheses are carried out before operations that are external to the parentheses, just like you'd expect. Beyond symbolic operators, Python contains a variety of named math functions available in the math module operator. To load a library into Python, import is followed by the name of the library. Some different math functions include the natural logarithm, square root, and the pi. Base Python contains a round function that lets you round numbers to the nearest whole number. You can also round up or down with the math.ceiling and math.floor function, respectively. Number 3, basic data types. A solid understanding of basic data types is essential for working with data in Python. Integers, or ints, TS for short, are whole number numeric values. Any positive or negative number, or 0, without a decimal is an integer in Python. You can check the type of a Python object with the type function. You can also use the function isInstance to check whether an object is an instance of a given type. The code output true confirms that 12 is an integer in the example shown above or below. If a math operation involving integers would result in a non-integer, which is also referred to as a decimal value, the result becomes a float. Floating point numbers, or floats, are numbers with decimal values. Unlike integers, floating point numbers don't have an unlimited precision because irrational decimal numbers are infinitely long, and therefore can't be stored in memory. Every number in Python with a decimal point is a float, even if there are no non-zero numbers after the decimal. Floats can also take on few special values, such as infinity, negative infinity, and not a number. Booleans, or bools, are true/false values that result from logical statements. In Python, Booleans start with the first letter capitalized, so true and false are recognized as bools, but lowercase true and false are not. You can create Boolean values with logical expressions such as the less than and greater than symbols, double equal signs to check equality, and an exclamation point with an equal sign to check inequality. And the words not and, or. Similar to math expressions, logical expressions have fixed order of operations. And the logical statement comparisons like less than and greater than and equal to are executed first, followed by not, then, and finally or. Text data in Python, also known as a string, surrounds text with single or double quotation marks to create a string. Two quotation marks right next to each other without anything in between them is known as an empty string. The empty string often represents a missing text value. For example, if you define a function that doesn't return anything, it will return none by default. And we can see that in the example given below. So the next section I will cover is data structures, such as manipulating strings, algorithms, exhaustive enumeration, approximation, bisection search, Newton's method, and functions. We are also going to see more details on how to process the data through more in-depth libraries such as NumPy, pandas, and reading and writing data. Variables. A variable is a name you assign a value or object, such as one of the basic data types that we learned about last time. After assigning a variable, you can access its associated value or object using the variable's name. Variables are a convenient way of storing values with names that are meaningful. In Python, assign a variable using the equal sign. In the example given, we assign x to an integer, y to a string, and z to the square root of 144. You can also assign the same object to multiple variables with a multiple assignment statement, which is why in the example we can set n and m both equal to 4. You can reassign a variable after creating it by assigning the variable name a new value. You can also assign several different variables at the same time using a comma-separated sequence of variables names, followed by the assignment operator and a comma-separated sequence of values inside parentheses. Lastly, extracting variables from a comma-separated sequence is known as tuple unpacking. List. A list is a mutable, ordered collection of objects. Mutable means that a list can be altered after it is created. You can, for example, add new items to a list or remove existing items. Lists are heterogeneous, meaning they can hold objects of different types. For example, the list we constructed holds a string, an integer, and a Boolean value. A list with no contents is known as an empty list. You can add an item to an existing list with the list.append function. Removing a matching item from a list. You can remove a matching item from a list with the list.remove function. You can also add a sequence to the end of an existing list with the list.extend function. As you can see, lists have many functions such as finding the length, max, and minimum, counting the occurrences of an object, and even checking whether a list contains a certain object. You can join two lists together with the plus operator, sort, and even reverse a list. Important functions of a list include indexing and slicing. Python sequences are zero indexed, so the first element of a sequence is at index position 0. The second element is index 1, and so on. This is why in the example, 0 is hello and 2 is bestest. We can also reverse the indexing by supplying a negative number. Therefore, -1 would be friend and -3 would be bestest. If your list contains other index objects, you can supply additional indexes to get items contained within the nested objects. Lastly, we can copy lists by slicing an entire list using the colon indexing operation. You can also copy a list using the list.copy function. Tuples and strings. Tuples are an immutable sequence data type that are commonly used to hold short collection of related data. For instance, if you wanted to store latitude and longitude coordinates of cities, tuples might be a good choice because the values are related and not likely to change. Like lists, tuples can store objects of different types. We can construct a tuple with a comma-separated sequence of objects within parentheses, which is shown in the following example. We can also construct a tuple by passing iterable into a tuple function. Tuples generally support the same indexing and slicing operations as lists, and they can also support some of the same functions, with the caveat of that tuples cannot be changed after they are created. This means we can do things like find the length, maximum and minimum of the tuple, but we can't append new values to them or remove values from them. Strings are technically sequences, immutable sequences of text characters. As sequences, they support indexing operations where the first character of the string index is 0. This means we can get individual letters or slices of letters with indexing. In the next section I will be covering is dictionaries and sets. A dictionary or dict is an object that maps a set of named indexes called keys to a set of corresponding values. Dictionaries are mutable, so you can add and remove keys and their associated values. Create a dictionary with a comma-separated list of key value pairs with curly braces is what we did in the example below. The keys would be the name indexes before the comma, and the values are what comes after. A dictionary's key must be immutable objects such as integers, strings, or tuples, but the values can be anything. You can access all keys, all the values, or all the key value pairs of a dictionary with keys, values, and items functions respectively. You can access all the keys and all the values, or all the keys value pairs of a dictionary with those functions respectively. Sets are unordered, immutable collections of immutable objects that cannot contain duplicates. Sets are useful for storing and performing operations on data where each value, Sets are useful for storing and performing operations on data where each value is unique. Create a set with a comma separated sequence of values with curly braces is what we did below. Sets do not support indexing, but they do support basic sequence functions like length, min, max, and sum. One of the main purposes of sets is to perform set operations that compare or combine different sets. Python sets support many common mathematical sets operations like union, intersection, difference, and checking whether one set is a subset of another. So the next section is NumPy arrays. The NumPy library is one of the core packages in Python's data science software stack. Many other Python data analysis libraries require NumPy as a prerequisite because they use its array data structure as a building block. NumPy implements a data structure called n-dimensional array or ND array. ND arrays are similar to lists in that they contain a collection of items that can be accessed via indexes. On the other hand, ND arrays are homogeneous, meaning they can only contain objects of the same type, and they can be multi-dimensional, making it easy to store two-dimensional tables or matrices. The as NP after the import statement lets us access the NumPy's library functions using the shorthand NP. ND arrays are homogeneous, meaning they can only contain objects of the same type, and they can be multi-dimensional, making it easier to store two-dimensional matrices. NumPy has a variety of special array creation functions such as np identity, np.I, and np.ones, np.zeros, etc. NumPy ND arrays offer numbered indexing and slicing syntax that mirrors the syntax for Python lists. Here's a picture and an example of what a NumPy array looks like. We can create 3D arrays which can store more objects than 1D arrays can. NumPys differ from lists because they can do so many more functions that lists are unable to do, plus work at a faster rate. There are two reasons why NumPy is faster: fixed type and contiguous memory. It is faster to read less bytes of memory and no type checking when iterating through objects. Contiguous memory allows all the data to be together in a NumPy, which makes it easier than lists. Pandas data frame, section 9. The Pandas library offers the data structures designed with this in mind: the series in the data frame. Series are one-dimensional labeled arrays similar to NumPy's ND arrays, while data frames are two-dimensional structures that essentially function as spreadsheet tables. Series are very similar to ND arrays. The main difference between them is with series, you can provide custom index labels and operations you perform on series automatically align the data based on the labels. A data frame is a 2D table with labeled columns that can hold different types of data. Data frames are essentially a Python implementation of the types of tables you'd see in an Excel workbook or SQL database. Data frames are the de facto standard data structure for working with tabular data in Python. You can create a data frame out of a variety of data sources like dictionaries, 2D NumPy arrays, and series using the pd.dataframe function. Here's an example of a dictionary being converted into a data frame. Next section, reading and writing data. Reading data into Pandas data frame is often the first step when conducting data analysis in Python. The pandas package comes equipped with several data reading and writing functions that let you read data directly from the common file formats, like comma-separated values in Microsoft Excel files. When you launch Python, it starts in the default location in your computer's file system, known as the working directory. You can check your current working directory by importing the OS module and then using the os.getCwd function. Other functions allow you to change the directory and list all of the objects in a directory. Data is commonly stored in simple flat text files consisting of values delimited by a special character like a comma or a tab. You can read CSV files into pandas data frame using the pandas function pd.read_CSV. Section 3, programming constructs. Although Python is a popular tool for data analysis, it is a general purpose programming language that wasn't designed specifically for that task. It is important to know some basic Python programming constructs so that you can write custom code and function to handle situations where built-in functions libraries fall short. Control flow. Programming constructs that let you alter the order in which code executes are known as control flow statements. The most basic control flow statement in Python is the if statement. An if statement checks whether some logical expression evaluates to true or false, and then it executes a code block if the expression is true. In Python, an if statement starts with if, followed by a logical expression and a colon. The code to execute if the logical expression is true appears on the next line, indented from the if statement above it by 4 spaces. For example, we use an if statement to see if x is greater than y. You can extend this basic if-else construct to perform multiple logical checks in a row by adding one or more else-if statements between the opening if and closing else. Each elif statement performs an additional logical check and executes its code if the check is true. In the previous example, by adding elif statements, we are increasing the amount of logical checks. We also can create for loops and while loops. The main difference being that for loops are best to use whenever you want to perform a specific number of operations, such as when running some code on each item in a sequence. While loops should be reserved for cases when you don't know how many times you need to execute a loop. For loops support a few special keywords that help you control the flow of the loop. Continue and break. The continue keyword causes a for loop to skip the current iteration and go to the next one. The break keyword halts the execution of a for loop entirely. Use break to break out of a loop. NumPy includes a function called where that lets you perform if-else checks on the sequence with less code. Not only is the np.where function more concise than a for loop, it is also more computationally efficient. And here's an example that when we use the np.where function. So the next section I want to cover is functions. The functions built into Python and its libraries can take you a long way, but the general purpose functions aren't always applicable to the specific task you face when analyzing data. The ability to create user-defined functions give you the flexibility to handle situations where pre-made tools don't cut it. Define a function using the def keyword followed by the function's name, a tuple of the function arguments, then a colon. We can see this in the example below where an addition function was made to sum two arguments together. Name functions are great for code that you are going to reuse several times, but sometimes you only need to use a simple function once. Python provides a shorthand for creating functions that let you define unnamed functions called lambda functions, which are typically used in situations where you only plan to use a function in one part of the code. In a lambda function, the keywords lambda is similar to def in that it signals the definition of a new lambda function. The values x, y are arguments of the function, and the code after the colon is the value that the function returns. Next section, list comprehensions. List comprehensions let you populate lists in one line of code by taking the logic you would normally put in a for loop and moving it inside the list brackets. We can construct the same list as the one above following the list comprehension. In a list comprehension, the value you want to append to the list comes first. In this case, number followed by a for statement that mirrors the one that we use in a for loop version of the code. You can optionally include if clauses after the for clause to filter the results based on some logical check. You can create dictionaries quickly in one line using a syntax that mirrors list comprehensions. Consider the following dictionary that sets words as keys and their lengths as values. We can also use zip inside a dictionary comprehension that lets you extract key value pairs from two sequences. The next section, data exploration and cleaning. This section aims to raise some of the questions you should consider when you look at a new data set for the first time and show how to perform various Python operations related to those questions. The first step in exploratory analysis is reading the data and then exploring the variables. It is important to get a sense of how many variables and cases there are, the data types of the variables, and the range of values they take on. We can use the shape, head, or describe function to get a sense of the data we are working with. After exploring the data for the first time, we should ask ourselves a few questions. Do I need all of the variables? Is there any unnecessary variables I need to get rid of? Should I transform any variables? Some of the variables may be encoded as data types that don't fit well with what the data really is or what it means. Are there any NA values, outliers, or other strange values? Missing values, outliers, and strange values can negatively affect statistical tests and models and may even cause certain functions to fail. Excuse me. Should I create new variables? The variables present when you load a data set aren't always the most useful variables for analysis. Creating new variables that are derivations or combinations of existing ones is a common step to take before jumping into analysis or a modeling task. Working with text data, section 15. String functions and pandas mirror built-in string functions that may have the same name as their singular counterparts. For example, string.lower converts a single string to lowercase, while series.string.lower converts all the strings in the series to lowercase. Panda also supports string.upper, and string.length. The string splitting and stripping functions also have Panda equivalents. You can combine all strings in a series together into a single string with series.string.cat. You can silence each string in a series and return the result in element-wise fashion with series.string.slice. A regular expression, or regex, is made of a sequence of characters and special meta characters used to match a set of character strings. Regular expressions allow you to be more expressive with string matching and operations than just providing a simple substring. A regular expression lets you define a pattern that can match strings of different lengths made up of different characters. For example, if we want to match any substring ending in ILL, we can use the function string.contains ill. Regular expressions include several special character sets that allow to quickly specify certain common character types. Some examples are lowercase a to z to match any lowercase letter and \d to match any digit. If we want to narrow down comments to those with only web links, we will need to match comments that agree with some pattern that express the textual form of a web link. We can do this by a simple regular expression to find the post with web links. Preparing numeric data. There are a variety of pre-processing tasks you should consider before using numeric data. Center and scaling. Numeric variables are often on different scales and cover different ranges, so they can't be easily compared. The simplest way to center data is to subtract the mean value from each data point. Subtracting the mean centers the data around 0 and sets the new mean to 0. Dealing with skewed data. The distribution of data, its overall shape, and how it's spread out can have a significant impact on analysis and modeling. Data with a long tail that goes off to the right is called positively skewed or right skewed data. When you have a skewed distribution like the one shown, the extreme values in the long tail can have a disproportionately large influence on whatever test you perform or models you build. Reducing skew may improve your results. Taking the square root of each data point or taking the natural logarithm of each data point are two simple transformations that can reduce skew, which you can see in the figures below. Highly correlated variables. In predictive modeling, each variable you use to construct a model would ideally represent some unique feature of the data. In other words, you want each variable to tell you something different. In reality, variables often exhibit collinearity. collinearity, a strong correlation or tendency to move together, typically due to the underlying similarity or common influencing factor. Variables with strong correlations can interfere with one another when performing modeling and muddy results. A positive correlation implies that when one variable goes up, the other tends to go up as well. A negative correlation indicates an inverse relationship. When one variable goes up, the other tends to go down. A correlation near 0 indicates low correlation, while a correlation near -1 or 1 indicates a large negative or positive correlation. Inspecting the data table, we see that the number of cylinders a car has and the weight have fairly strong negative correlations to gas mileage. This indicates that heavier cars and cars with more cylinders tend to get lower gas mileage. Imputation describes filling in missing data and estimates based on the rest of the data set. Usually values are imputed based on the mean. Next section, merging data. Data is often split across several tables that you need to combine in some way. Data frames can be joined together if they have columns in common. Joining tables in various ways is a common operation when working with databases, but you can also join data frames in Python using functions included with pandas. A unique identifier, such as ID, is usually a good key for joining two data frames together. In the example below, we combine the two tables with the P_ID column. An inner join only merges records that appear in both columns used for join. A left join keeps all key values in the first or left data frame. A right join keeps all the values in the second or right data frame. And an outer join keeps all the key values in both data frames. Frequency tables, section 19. Frequency tables is discovering relationships between variables is a fundamental goal of data analysis. Frequency tables are a basic tool you can use to explore data and get an idea of the relationships between variables. A frequency table is just a data table that shows the counts of one or more categorical variables. Create frequency tables, also known as crosstabs, in pandas using the pd.crosstab function. There are two different types of frequency tables, one-way tables and two-way tables. One-way table takes one or more array-like objects such as indexes or columns and then constructs a new data frame of a variable based on the supplied arrays. We can make a crosstab to see how many people survived on the Titanic. Two-way frequency tables, also called as contingency table, are tables of counts with two dimensions where each dimension is a different variable. Two-way tables can give you insight into the relationship between two variables. To create a two-way table, pass two variables to the pd.crosstab function instead of one. An example would be to see the relationship between survival and sex. The crosstab function lets you create tables of more than two categories. Higher dimensional tables can be a little confusing to look at, but they can also yield finer grained insight into interactions between multiple variables. You can create a higher dimensional table by adding more columns. The next section, plotting with pandas. Visualizations are one of the most important and powerful tools at your disposal for exploring data and communicating data insights. The pandas library includes basic plotting capabilities that lets you create a variety of plots from data frames. Plots in pandas are built on top of a popular Python plotting library called matplotlib, which comes with the Anaconda Python distribution. Below includes some examples of plots that pandas offers, and I will be briefly going over each one. Histogram. A histogram is a univariate plot, a plot that displays one variable that groups a numeric variable into bins and displays the number of observations that fall within each bin. A histogram is a useful tool for getting a sense of the distribution of a numeric variable. Below is an example of a histogram coded within Python Jupyter's Notebook. Box plots. Box plots are another type of univariate plot for summarizing distributions of numeric data graphically. An example is shown of a box plot of a carrot using the pd.boxplot function made side-by-side box plots. A side-by-side box plot takes a numeric variable and splits it based on some categorical variable, drawing a different box plot for each level of the categorical variable. And you can see the side-by-side box plot on the right and the regular box plot on the left. Density plots. The density plot shows the distribution of a numeric variable with a continuous curve. It is similar to a histogram, but without discrete bins. A density plot gives us a better picture of the underlying shape of a distribution. We can create a density plot with the series.plot, and we have to make sure to specify the kind is equal to density, and we can see that plot below. Bar plots. Bar plots are graphs that visually display counts of categorical variables. We can create a bar plot by creating a table of counts for a certain variable using the pd.crosstab function, and then passing the counts to df.plot kind, and we have to make sure the kind is specified to bar. You can use a two-dimensional table to create the stack bar plot. Stack bar plots show the distribution of a second categorical variable within each bar, and we can see the regular bar plot on the left and the stack bar plot on the right. Scatter plots. Scatter plots are bivariate, two variable plots that take two numeric variables and plot data points on the XY plane. To create a single scatter plot, use the df.plot and make sure to specify the kind as scatter. Line plots. Line plots are charts used to show the change in a numeric variable based on some other ordered variable. Line plots are often used to plot time series data to show the evolution of a variable over time. Line plots are the default plot type when using df.plot, so you don't have to specify the kind of argument when making a line in pandas. And I forgot, sorry, saving plots. If you want to save plots for later use, you can export the plot figure to a file. First, get the plot figure with plot.get_figure, and then save it to a file with figure.savefig, and then the file name. You can save plots to a variety of common image file formats such as PNG, JPEG, and PDF. Section 5. This section covers the fundamental of basic statistics and how to calculate them in Python. Descriptive statistics. Section 21. Descriptive statistics are measures that summarize important features of data, often with a single number. Producing descriptive statistics is a common first step to take after cleaning and preparing a data set for analysis. Some examples being the mean and median of data. Measures of center are statistics that give us a sense of the middle of a numeric variable. In other words, centrality measures give you a sense of a typical value you expect to see. Common measures of center include the mean, median, and mode. In a symmetric distribution, the mean and median will be the same. In the plot below, the mean and median are both so close to zero. They're both so close to zero that the red median line lies on top of the thicker black line drawn at the mean. And you can see that on the left for the normal distribution. In skewed distributions, the mean tends to get pulled in the direction of the skew, while the median tends to resist the effects of the skew. The mean is also influenced heavily by outliers, while the median resists the influence of the outliers. Measures of spread, dispersion, are statistics that describe how data varies. While measures of center give us an idea of the typical value, measures of spread gives us a sense of how much the data tends to diverge from a typical value. Before I continue with measures of spread, I just wanted to point out that we can see how the mean is affected by the outliers and by skewed distributions, which is why the blue line, which is the mean, is more towards the skew or more towards the outliers, when the median is more approximately closer to the middle, which is the orange line. One of the simplest measures of spread is the range. Range is the distance between the maximum and minimum observations. And we can see we calculated in the code with by doing the max subtracted by the min. Box plots are a good visual representation of the 5-number summary in the IQR. Probability distribution, section 22. Many statistical tools and techniques used in data analysis are based on probability. Probability measures how likely it is for an event to occur on a scale from 0 to 1. 1 being the event always occurs. In statistics, there are a range of precisely defined probability distributions that have different shapes and can be used to model different types of random events. The uniform distribution is a probability distribution where each value within a certain range is equally likely to occur, and the values outside the range would never occur. If we make a density plot of a uniform distribution, It appears flat because no value is any more likely to occur than the other. When you need to generate random real numbers in a range with equal probability, you can draw numbers from a uniform distribution using stats.distribution.rvs. Python also comes with a library called random that lets you perform various operations that involve randomization. You can ensure that your results are the same each time you use a function that involves randomness by setting the random number generator seed value to initialize it prior to running the function. There are also other distributions that Python allows you to create, such as the normal distribution. The normal or Gaussian distribution is a continuous probability distribution characterized by a symmetric bell-shaped curve. A normal distribution is defined by its center, which is its mean, and spread, which is its standard deviation. The binomial distribution is a discrete probability distribution that models the outcome of a given number of random trails of some experiment or event. The binomial is defined by two parameters: the probability of success in a given trial and the number of trials. Geometric and exponential distributions models the time it takes for an event to occur. The geometric distribution is discrete and models the number of trials it takes to achieve a success in repeated experiments with a given probability of success. The exponential distribution is a continuous analog of the geometric distribution and models the amount of time you have to wait before an event occurs to give a certain occurrence rate. The Poisson distribution models the probability of seeing a certain number of successes within a time interval, where the time it takes for the next success is modeled by an exponential distribution. Confidence interval, section 23. Statistical interference is the process of analyzing sample data to gain insight into the population from which the data was collected and to investigate differences between data samples. Point estimates are estimates of population parameters based on sample data. The sample mean is usually not exactly the same as the population mean. The difference can be caused by many factors, including poor survey design, biased sampling methods, and randomness inherent to drawing a sample from a population. Our point estimate based on a sample of 500 individuals underestimates the true population mean by 0.6 years, but it is close. This illustrates an important point. We can get a fairly accurate estimate of a large population by sampling a relatively small subset of individuals. A point estimate can give you a rough idea of the population parameter like the mean, but estimates are prone to error, and taking multiple samples to get improved estimates may not be feasible. A confidence interval is a range of values above and below a point estimate that captures the true population parameter at some predetermined confidence level. Calculate a confidence interval by taking a point estimate and then adding and subtracting a margin of error to create a range. Margin of error is based on your desired confidence level, the spread of data, and the size of your sample. The way you calculate margin of error depends on whether you know the standard deviation of a population or not. If you know the standard deviation of population, the margin of error is equal to the formula on the left, where sigma is the population standard deviation, n is the sample size, and z is the number of known as the z critical value. We can also make a confidence interval for a point estimate of a population proportion. In this case, the margin of error equals the formula on the right, where z is the z critical value for our confidence level, p is the point estimate of the population proportion, and n is the sample size. Notice in the plot above, all but one of the 95% confidence intervals overlap the red line, marking the true mean. This is expected because we get a 95%, we should get a 95 confidence 95% of the time. So this is why it only misses 5%. Inferential statistics. Inferential statistics are used to draw inferences from a sample of a huge data set. We will explore the basic principles behind using data for estimation and for assessing theories. Hypothesis testing, section 24. Point estimates and confidence intervals are basic inference tools that act as the foundation for another inference technique. Statistical hypothesis testing. Statistical hypothesis testing is a framework for determining whether observed data deviates from what is expected. Python skippy.stats library contains an array of functions that make it easy to carry out hypothesis tests. Statistical hypothesis tests are based on a statement called the null hypothesis that assumes nothing interesting is going on between whatever variables you are testing. The exact form of null hypothesis varies from one type of test to another. If you are testing whether groups differ, the null hypothesis states that groups are the same. The purpose of the hypothesis test is to determine whether the null hypothesis is likely to be true given a sample data. If there is little evidence against the null hypothesis given the data, you accept the null hypothesis. If the null hypothesis is unlikely given the data, you might reject the null in favor of the alternative hypothesis that something interesting is going on. The t-test is a statistical test used to determine whether a numeric data sample differs significantly from the population of whether two samples differ from one another. The one sample t-test. A one sample t-test checks whether a sample mean differs from the population mean. Here's an example we use that includes data for the population of voters in an entire country and a sample of voters in Minnesota, and test whether the average age of voters in Minnesota differs from the population. The test result shows that the test statistic t is equal to negative 2.574. This test statistic tells us how much the sample mean deviates from the null hypothesis. If the t statistic lies outside the quantiles of the t distribution corresponding to our confidence level and degrees of freedom, we reject the null hypothesis. Two sample t-tests investigates whether the means of two independent data samples differ from one another. In a two sample test, the null hypothesis is what the means of both groups are the same. Unlike the one sample t-test where we test against a known population parameter, the two sample test only involves sample means. Here's an example of the voter age data in Wisconsin to test it against the sample we made earlier. Pair t-test. The basic two sample t-test is designed for testing differences between independent groups. The pair t-test lets you check whether the means of samples of the same group differ. Section 7. Predictive modeling. Predictive modeling is the use of data and statistics to predict the outcomes of data models. We will see this through linear regression and logistic regressions. Linear regression, section 27. Linear regression is a predictive modeling technique for predicting a numeric response variable based on one or more explanatory variables. The term regression in predictive modeling generally refers to any modeling task that involves predicting a real number. The term linear and the name linear regression refers to the fact that method models data with linear combination of explanatory variables. Using a linear model generated from the empty cars data, we can plot the line it fits on our scatter plot to get a sense of how well it fits the data. The regression line looks like a reasonable fit and it follows our intuition. As a car weight increases, we would expect the fuel economy to decline. Outliers can have a large influence on linear regression models. Since regression deals with minimizing squared and residuals, large residuals have a disproportionately large influence on the model. Variables often exhibit nonlinear relationships that can't fit well with a straight line. In these cases, we use a linear regression to fit a curved line data by adding extra higher order terms to the model. A linear regression that involves higher order terms is known as a polynomial regression. A quadratic function seems to fit the data a little bit better than the linear one. Logistic regression, section 28. Logistic regression basics. Logistic regression is a classification method built on the same concept as linear regression. For linear regression, we take linear combination of explanatory variables plus the intercept form to arrive at a prediction. Logistic regression takes a linear combination of explanatory variables plus the intercept term, just like a linear regression, but then takes the result and passes it through a logistic function. The logistic or sigmoid function used for logistic regression is defined as the equation shown on the right, where t is the same linear combination of variables. It's also defined as this equation, where t is the same linear combination of variables using linear regression, and the sigmoid function looks like an elongated S when plotted. We can use logistic regression model to predict survival The table. Sorry, I don't know why my computer's lagging. The table shows that the model predicted a survival chance of roughly 19% of males and 73% of females. If we use this simple model to predict survival, we end up predicting that all women survived and that all men died. Section 8 from ENBC 403, an introduction to the fundamentals of conducting research projects utilizing a general understanding of quantitative and qualitative research, clinical data analysis, and multiple examples of different research approaches in biological phenomenon. Decision trees, number 23. We would like to make this scatter plot splits into multiple parts. Where and how these splits are conducted is within its algorithm, which involves looking at information entropy. It projects the information increasing by the points and adding to the values of the split points. Algorithm will stop when the minimum certain information is attained, and we can't add any more information to the setup by splitting these leaves, often 5% of total points. Also, final leaves are called terminal leaves, and here's a few examples of that. Random forest. A random forest model is a collection of decision tree models that are combined together to make predictions. When you make a random forest, you have to specify the number of decision trees you want to use to make the model. The random forest algorithm then takes random samples of observations from your training data and builds a decision tree model for each sample. And here are some of the examples below. Why is it called random? Because of bootstrapping and random feature selection. Why bootstrapping and random feature selection. Why bootstrapping and feature selection? It ensures that we are using the same data for every time training. This makes our model less sensitive to original data. What is the ideal size of features to be considered? We took 2 features, which is close to the square root of total features. And then how to use it for regression problem? While combining the predictions, just like the average, it's all set to use it for regression. So that's the end of my presentation. I just want to say some of the outcomes we got from this course is to appreciate the science and statistics and scope of its potential applications, to be able to summarize and present data in meaningful ways, to be able to select the appropriate statistical analysis depending on the question at hand, to be able to conduct, present, and interpret common statistical analysis using R, and be able to effectively and clearly describe results from analysis performed to others. And some skills we gained was data analysis, data visualization, Python programming, making machine learning modules. So thank you so much for being a professor of this course. I hope you enjoy the rest of your summer.